by cycle in the Kazoo complex for some module M, then you get a cycle in this Kazoo complex for the module M.
This multiplication, like as M is model over Kazoo complex, and it's just multiplication by it. Yeah.
Well, as I said, this is a module, right?
Yeah,
you can multiply
multiplication.
an element from the module to the element of the algebra. And the claim is just saying that if d of this thing is 0, d of this thing is 0, then you apply the product rule.
Mm-hmm.
Well, yeah, saying that this is a DG module, it means that I have a product rule for the, so there is a differential depending on the f and m, and if you apply this to the product, say you have some x which is m, where m belongs to the complex, to this Kazoo complex, you have the standard product rule, meaning that we first apply this differential to the x, take product with m, or as before, up to sign, you first, or you skip x and apply the differential now. Well, sorry, the first differential is of course just on the complex without m. So this is the standard differential, and then we have differential in the Kazoo complex with the module. So of course you can check this property immediately, but this is part of the definition of a DG module. It means that you have action of this algebra on the graded module, plus you have this.
Элемент x, крышка m, это будет элемент тоже k с точкой fm?
Yeah, sure. Oh, well, what's an element here? This is precisely the wedge product of several elements from the L tensor, element from the M, right? So clearly, if I just multiply by another wedge product of some elements in the L, this is of the same form, and that is how you multiply element from this module by the element of this algebra. Yeah. So this is a simple exercise in the product rule. So this product rule for the module, and there are two also quite easy exercises. If you multiply cycles by the boundaries, you will get boundaries. Now I multiply by a cycle on the left, but I can also do this on the right. So I think immediately as I do this statement, you see how to prove it. That's quite easy statements. But why I'm writing this, that because I have a interesting conclusion. So in particular,
Что означает, что z от f домножить слева на b от fm? То есть как?
You mean what's the difference here?
Да.
There is no much difference because, well, this is a supercommutative algebra. The left and right is more or less the same, but, well, kind of formally you can define this. We can multiply this on the right, but what you really means if you multiply this on the left, but you need to kind of change the sign because you move this around the wedge product of several elements. So up to a sign is actually the same action. Sign the left and right actions coincide. These two actions. So in particular, I can say that the cycles is a graded subalgebra. Subalgebra. And the boundaries, looking at the last derivations, this is a two-sided ideal. But again, this is supercommutative situation, so I can say this is an ideal. So this is an ideal, and this means that the homology that I'm going to write just h of f, maybe I just need to introduce this notation somewhere here before the preposition. So the homology, say, depending on the F and M, well, this is just by definition, you take homology of the causal complex. And the same for homology for the homological causal complex. So then the homology is a graded commutative algebra. So commutative, let's say this is part 2 of the preposition. So the homology graded commutative algebra.
B с точкой от F это идеал Z с точкой от F.
Yep. Well, this is precisely this two last two relations. Yeah, so this is a graded commutative algebra. This is just kind of the long explanation why I can say that the homology form a graded commutative algebra. And 3, which I'm going to leave as an easy exercise, that if you take homology of the causal complex for the module M, so this is a module over homology or just causal complex without module M. So this is easy. But also from this proposition you can notice the following, that H, say I, for F and M is an R modulo I module, where the ideal I is by definition is just the image of the linear form F. Right? In particular, even more specifically, we can even compute what a zeros homology. So zeros homology will be just the quotient of the M by the IM. So a special case, of course, zeros homology of the ring R is just the quotient of the R by this ideal. But do you see why all this homology are actually R mod I modules? This means that the ideal is acting trivially on these modules. Right. Well, for example, you can look at the second identity that I wrote. Now, what is the ideal I? Ideal is exactly B0. Hence, when you multiply a cycle by B0, you'll get a boundary. Meaning that when you act on the quotient of the cycles by the boundaries, you'll get a zero action. So in fact, all causal homology modules, or the same is called homology, are all R modulo I modules. So they are only supported for the variety which is given by the ideal I.
А правда ли, что это утверждение верно для любой державы? Проводишь?
Sure, yeah. I think it is, yes. Okay. Now I want to kind of take a different viewpoint on this little result. And this different viewpoint is the following. So kind of observation, maybe on my list of trivial observations, I don't want to call this proposition, so I'm just going to put a bullet for every new observation. So first easy observation is the following, that if I set by definition count A to be f of x, x of x, so this is in the ideal, but x is in the module L. So then I have the following formula. Multiplication, that I'm going to write mu A. So this is the differential composition to the exterior product with x plus the other way around. So I have first exterior product with x, and then I take the composition with the differential in the causal complex. Here, this notation mu A, if I want to apply this to some t, this is just by definition at. So mu is for multiplication of A. So operation of multiplication on any element in this ideal by this formula is homotopic to zero. Right, so, in other words, mu A is homotopic to zero.
Why is mu A of t is at?
By definition.
But
That's the definition. So just mu A is just one of the notations for multiplication. You can just as well write 8 here. Just won't be clear.
so the observation is that multiplication is homotopic to zero by this homotopic.
Yeah, so essentially the observation is that we have this formula.
Ah.
And if you interpret this formula from the point of view of homological algebra, you see this is exactly homotopy for this map. Right, so this thing is a homotopy that makes this map multiplication of A homotopic to zero. And there's the question why this formula is true. Yeah, this is just a product rule. Imagine that you have some z, you plug in z here, apply the differential by the product rule, right? So x is just an element of degree 1. Well, you get some cancellation, right? So you get df applied to x, which will precisely give you 8.
Mm.
And then the second term, because this is degree 1, you give you additional minus, it cancels with this term.
Mm.
So just a very simple product rule.
Mm.
Okay, so multiplication on any element from the ideal is homotopic to zero. And of course, you can look at other two maps. So you can take this multiplication on A, take a tensor product with M, and this is still no homotopic. So let me write two maps together. So we have this thing and we have take home into M. So these are also homotopic to zero. So in other words, on any four versions of the complex that we consider, with module, without module, homological, multiplication by any element in the ideal is homotopic to zero. Well, what it tells us, well, for example, from this observation, you can also immediately observe that again this is true, which is another proof that all the homological modules will be supported on the R moduli, because I will be acting trivially. And another observation that if, for example, if I is equal to R, in the degenerate case, then all four Azul complexes are contractible, meaning zero in the homotopic category. Right. I guess it's clear because now in the ideal I have 1, right, and 1 is homotopic to 0 by these observations. So that's a contractible complex by definition.
What do you mean all four causal complexes?
Well, that's all these versions that I discussed. Well, two versions are without module, just for form, and you have homological and cohomological, and then you have a module. So these are four versions that I'm talking about. Okay, so this is one easy observation, another easy observation, but it is still quite useful, as we see later, that if we have two modules and two linear maps, so here I have F1 map from the module L1 to the R, and F2 is a map from module L2 to the R. Then of course we can define a sum of these maps. Let's call this F. So F is a map from the L1 plus L2 to the R. And by definition, F on the pair x1 is 2. Well, I just extend this kind of, I have a map on the two sums and can extend this to the direct sum. This is just sum. This is F1 and F2. Okay. So this we can do, and then the claim is that if you take the Gaussian complex for the F, take a tensor product with the F1, take a Kazoo complex for the F2, take the tensor product of these two Kazoo complexes, you get a complex which is isomorphic as a complex to the Kazoo complex for the sum. Right, well, again, I want to say this is a completely trivial observation because, first of all, without the differential, and this is just the property of exterior algebra. If you take a tensor product of two exterior algebras, you get an exterior algebra for the sum of these two modules. So without differential, this is something that you're supposed to know from the first year. And with the differential, again, you can check immediately that the differential on the left and on the right is the same, because well, you compare them, for example, on degree 1, they are the same, and then if you by the product rule, you can set everywhere. Okay. But this gives us an important special case, and that we're going to use all the time, that if you have L to be just a free module, then of course the linear form is just a sequence of sequence of elements of the ring. So let me say that the xi is the image under the map F of the basis, right? When I write that L is isomorphic to this free module, I can as well say that I choose a basis in the L. So this is the basis. Apply F to every basic element, I get some xi in the ring. So this is in the ring. Now, just by the very elementary algebra, how we can describe a form on the free module, that's precisely just what's supposed to be a column. No, I think this is supposed to be a row of elements. So this is the row of elements. Okay. So what, applying what we already know, we can say that the Kazoo complex for F, which I'm going to write when I have this special situation of a free module, I'm going to write this just as the X underlined. So this is the same as the tensor product of the Kazoo complexes for individual xi. Okay, so just notation. X underlined is just a list, a sequence of the elements x1 up to xn. So this is exactly the same thing for free modules. Okay, so next, if you have a free resolution F for the, say, R module I, or you can do modifications. Now I'm mostly talking about the main Kazoo complex, but you can, if you want, you can immediately modify everything when you have a module. Now, if this is a free resolution, so this is a complex. For a free resolution, we can lift the identity. So we have identity on the R module I, and then the lift of the identity is some map that I'm going to call phi. So this is a map from the Kazoo complex for a sequence to the resolution F. Okay, notice that of course that when I introduce this notation, xi is just the image of the basic elements. Of course, the ideal that I abstractly introduced before as the image of F is precisely ideal generated by this sequence. So we have this lift, which is of course unique up to homotopy.
Can you repeat, как мы получили это отображение фи?
Well, this is just a standard homological algebra. Well, you have a resolution by free modules. In fact, it could be projective modules. The argument is the same. And then we have another complex, again, of free modules. But it would be enough to have. I think in most general setting, it would be enough to have projective modules in this complex and any resolution by any modules in this complex. And then you just lift the map kind of step by step using projectivity property. I'm just using standard construction
Yeah, but
homological.
we didn't say that Cajou complex for free module is a resolution of error quotient by I.
But it is not a resolution, and it don't have to be a resolution. To apply this property, you don't need to you don't have two things to be a resolution. See, one of them has to be a resolution by any modules, and the other has to be a complex of projectives. Because essentially, what you do is just use the property that is projective to construct the step by step.
I'm not sure if that both could be only just projective modules.
Oh, now in our case, they both even free modules, so it's not a problem. But in homological algebra, we have more general statement. Okay, so there's this lift unique up to homotopy, and this, of course, induces a natural maps from the homology of the Cazaux complex. Say, now just take a tensor product with M, and take a tensor product phi tensor product with the identity on M. And then I'll get the canonical maps from the homology to the cohomology, sorry, from the homology on one complex to the homology of the other complex. And I can also dualize everything to the M, and then I'll get the canonical map in the other direction. So from the X I R modulo I M to the cohomology of the cochain Cazaux complex. I don't think that existence of these two maps will play any role in what I'm going to discuss. Just one remark. Okay. Finally, I think then what I'm going to say now is a little bit more useful. So here we have an orientation. So orientation on a free module L, which we can identify with the R to the M. Is unique isomorphism. I'm going to call omega n from the top exterior power of L to the R. So potentially we have many such isomorphisms, but this is unique if I require that this orientation on the product of all basis elements by the orientation is mapped to the one. So, and then we can extend this omega n kind of descending to the omega I. So I can say that there are maps omega I from the ith exterior power of the L to the exterior power with the index n minus I of the L, and I need to take the tool. Right, so this the map is defined as follows. If I try to compute omega I on some element x, right, so this is supposed to be some form, so I can apply this to some y. So in this computation, x is in the wedge IL and y is in the wedge n minus IL. So then I do the following. I just take the product of these two elements, x wedge y, and then to the product, which lives in the top exterior power, I can apply the orientation. So omega n. So this is definition. And you can check immediately that this is an isomorphism, of course, for the free modules. But for example, this is clearly an injective map. Let's say the free modules of this of the same ring. Well, it's also quite really. No, if you want, you can just write the basis here, here, and check this in the basis.
Это то, что называется звездочкой Ходжи.
No. No, for the Hodge star, you need to have a bilinear form. So usually this is used in differential geometry and you have something like Riemannian to the Riemannian metric. So here I don't choose a form. Instead I'm choosing orientation. So what you're saying is something like a Riemannian version of the story. I'm telling you the Calabi-Yau version of the story.
And I think in differential geometry, what we need from metrics is orientation to define Hodge star.
Yes, I'm sure. I think you might be correct. If you make a metric, you automatically can get a volume form, right? And volume form give you the orientation. Yes, so.
Is it true for exterior algebra for models that when we take dual, they say that it is isomorphic to
Sure, yeah.
exterior product?
This is true, of course, in our situation because this is just a free module. And if this is not free, right, so this is important for this isomorphism. And if this is not free, well, I don't think so. No. Okay. Yeah, maybe I just mentioned that if you want this in terms of the formulas, you can write the formula. So if you apply omega I to the monomial with the multi-index capital I, and you want to compute this on another monomial with the multi-index capital J, well, this will be, if you do the computation, 0 if I intersect with J is not empty. And it will be some sign, so let me do this sigma ij. I'll explain this in a second. If the intersection is empty. So this sign is the following, which I think with this definition maybe you can avoid these cases even. So if you multiply two monomials, well, potentially you'll get sign of a permutation if you just take a union of the two multi-indices. So this is precisely the sign that we have. So up to a sign, everything is completely clear. Okay, so now we have a following situation. We have a Kazoo complex. Let me just write this explicitly. I have 0, I have the top exterior power, then we have the differential. Just for shortness on this picture, I'm going to write D for the Kazoo differential. This goes to the exterior power of degree n minus 1. Differential, done. So finally I'll get L, and in the 0th degree we have ring R. So then we have a dual of the Kazoo complex. R. So when you dualize, the dual differential goes in the other direction, so this goes to be R L star, D star. So here we get L to the exterior power n minus 1, dual, and finally here on the last part you'll get top exterior power of the L and dual.
We still work when L is free.
Yes. Yes, L is free. Yeah, I think for the rest of today's lecture L is free. Because now I have maps and induced by the orientation. Right? Well, I have a question for you. For example, can you guess what's the dual of the Kazoo differential?
So wedge with dual to F.
Yeah, so in our case now, form is just a row of elements, so I can as well say that this is wedge product with the X. I want to compute this on something, I need to take the wedge product. Just explicitly do the computation, right? So, this is just rule map, explicitly computed rule map. See what it's doing. So I'm going to leave this as an exercise. And with this simple observation, there is another observation, which is just explicit computation. That if you look at the commutative squares, well, look at the squares that I have on this diagram, well, they are not commutative, but they are almost commutative. So the formula is that they are commutative up to a sign.
When you say that d lower star is wedge product with x lower bar, x lower bar is the element of what degree?
One.
One. And how? Like x lower bar is the row of elements.
Yeah.
So it's like sum of it, sum of wedge products.
Well, you can think about this just as a well, it was a form on the module, right? So you can think about this as just an element in the dual module, right? And here you just stated you have some y that lives in the omega I dual, right? And then it makes sense to take such wedge product, and this wedge product is of course living in the lambda I plus one. No.
Yes.
And of course you can see immediately that the square of this thing is of course 0, as it's supposed to be. But there is no product rule for this element, of course. It's a little bit different. Okay. So what I'm going to say that the square that we have in this diagram is almost commutative. So if I just modify this definition of the omega I slightly, let me say that the tau I is just minus 1 to the power I times I minus 1 over 2 omega I. Then this is an isomorphism. So if I look at this as a map from the Kazoo complex on the bunch of elements to the Kazoo, from the chain Kazoo complex to the co-chain Kazoo complex on the same elements, then this is isomorphism of complexes. And more generally, this isomorphism induces you an isomorphism when you take a tensor product with M or you take home into M. So maybe I do this computation. So for example, let's look at the co-chain Kazoo complex for the sequence of elements X and some module M. Well, by definition, we know that this is home from the chain Kazoo complex into module M. Now, this thing is isomorphic to the home of the Kazoo complex into R, and then you take a tensor product with M. It's probably the only non-trivial observation in my computation. Why we have such an isomorphism here? We need to use one of the properties of the Kazoo complex. It won't be true for any complex. For which complex I can say that if I take a home from the complex to a module, then this is tensor product of the home to the ring, tensor with the module.
Like, not for free, it's true, I suppose.
If it's just free, I still don't think this is true. I don't even think that this is true when you have just one free module. There's one more thing you need to say.
Конечность какая-нибудь.
Yep. So this is true if the complex you consider is complex of finite projective modules. Because this isomorphism, for example, if this is just a module, to say this is true, well, at least you need this to be finitely generated projective. So if you have a finite complex of finitely generated projectives, then this is still true. This is true on each individual module, and of course this is true for differentials.
Why it's true for individual module?
I'm using something from commutative algebra. Well, the exercise, if you wish, is the following: that the P is finitely generated projective if and only if the Hom from P to M is isomorphic to the dual of the P, which is Hom from P to R, then Z M. So projective modules are precisely the modules that are nice with respect to the dualizations.
And why we need the finitely generated?
Well, if this is not finitely generated, this is clearly not true. Well, even for vector spaces.
Yeah, that's true.
So if you have, yeah, for if M is just a K, this is infinite dimensional vector space, then, well, no, then this is fine. Well, but if you take this to be the same, then these two things are definitely different. Okay. So yeah, so this is what we use, this little exercise from commutative algebra. Well, actually, okay, let's say this commutative. Okay, so, but then the rest of the computation is simple. So if I say that this is isomorphic to star, then the star, I can replace this by the k lower star of x, right? Then the product is.
Supposed to be upper dot.
Well, I'm doing two things. First of all, by the definition, this is k with the upper bullet, right? But I already have this isomorphism, so I can replace this with the k with the lower bullet. Okay, and finally, this is again just the last step. This is the definition of the kxm. So you see that we derived the duality when we have coefficients in M. Yeah, and if you look at this duality, notice that we have kind of shifted everything. Well, this is say in degree n, this is in degree 0. So if we account for this, then we will get the isomorphism that the Kazoo homology for the sequence X with coefficients in the module M is isomorphic to the Kazoo cohomology, but we need the shift by the n. So this is subduality of the Kazoo complex. All these properties can be called subduality of the Kazoo complex. So of course this is all true for a free situation, but the way I know how it's usually used, for example, in algebraic geometry, you take a vector bundle, like a modularly coherent sheaf, then you take a section, and then you just form this Kazoo complex for vector bundle and a section, just taking the exterior algebra and extending this section as the differential satisfying product rule. And then the question is, of course, when this is, for example, acyclic, and this gives you resolution, so you analyze this locally. As simplicity, you can localize it every prime ideal, and then you get something the Kazoo complex over a local Pythagorean ring, and so this will be a Kazoo complex for the free module, and then you just do this locally, and if localization at every prime ideal will give you a regular sequence, so the set is will give you a regular sequence, you call this section of vector bundle a regular section, so regular sections give you resolutions. So typical applications can reducing everything to the free situation of a local ring. And this is what we're going to do. We're going to prove that actually this works in this situation. So when we have a regular sequence, so this is a regular sequence, then this will be resolution, free resolution for the R modulo this regular sequence.
How does
Section give us F, which we need for causal complex.
Well, what's a section? If you have some coherent sheaf living on some X, a section is just a map like this. So, in other words, this is a map like this. This is a linear form I started with in applied case at the beginning of the lecture.
Yeah, we usually take section of dual vector bundle, and we'll get causal complex for just the vector.
So we have causal complex for dual.
Yeah, so in algebraic geometry, if you start with a section of the E, then the causal complex will be exterior algebra of the dual vector bundle. Okay. Finally, last of the trivial observations. Easy, but I think it's important. So suppose we have a short exact sequence of modules. It's a short exact sequence of R modules. Then I claim that we have short exact sequences of complexes. So one more tautological property. Okay, question, why this is exact? So this is short exact sequence of complexes. Again, we need something from the causal complex. It won't be true for any complex.
Well, for the first row, it's trivial. Like for the row where we have just M prime, M double
Yeah,
prime.
were you meaning that we have the degree 0 in the causal complex that we just
Yeah, it's degree 0.
Yeah,
That's trivial.
sure. Well, the reason this is trivial because you have just the ring R in the degree 0, right? Does the
Yes.
product with R doesn't do anything. What if you go to the degree 1?
Yeah, well, on the row it's trivial because that's all is free it's
Yeah.
free modulus. But why it's commutes with the differentials? That's
No, the reason this is that you commute with the differential is quite simple. This is the reason that what we just do, we just take a tensor product with the complex and the tensor product is a function.
yeah, that's true.
So commutativity of all these squares to get is trivial. What is not trivial, what would be the general requirement for the complex to get this, right? So we have this thing, you take that tensor product as a complex. What you really need is just that individual terms in this complex are flat modules. Then you get exactness in each of the degrees, right? Because just take that as a product with the flat modules. And the commutativity is obvious. Okay. So this is the end of the list of the trivial observations. Now let's do something less trivial that requires actually proof. So let's see be a chain complex. So let's see be a chain complex of R modules. X is an element in the ring R. Then we have the following. 3 statements. So the first statement is that when you take a tensor product of the complexes, first is just the causal complex on one element X, and second is the given chain complex. And this is isomorphic to the cone of the map from the complex to itself, given by the multiplication on the by the element x. So this is cone of the map multiplication on x. So I'm going to comment during the proof what is cone and how we get the cone, of course. So if you don't remember the definition and don't know the definition, it's not a problem. I will say what we need to know. So then, in the induced long exact sequence of homology, for the short exact sequence of complexes, which we have. So I'm guessing I'm saying that first of all I have the short exact sequence of complexes, and then for this short exact sequence of complexes I can look at the long exact sequence of homology. I have the following claim that the connecting
Is there C dot to the minus 1? Isn't it should be 1?
no, it's -1. We will see in the proof that this is how it works. The reason is that for any map of two complexes, you get this short exact sequence of complex if you put the cone in the middle. But now we know that the cone is this thing,
Yeah,
so
but,
just
I understand that, but I suppose for cone it should be 1. Just,
+1.
yeah, it should be +1, not -1.
Well, this will be just a shifted cone. Well, you need to put shift somewhere. It cannot be C and C, definitely. And then there are, I think, as many conventions as many texts. So you can shift this, you can kind of reorder this. We will come to this. So the claim is, the important claim in the part 2 is that the connecting homomorphism, so the connecting is for short is map. So say this is del, and this will be hi minus 1 of the C to the hi minus 1 of the C. Notice that my connecting map is correct because I have this shift -1. So this is indeed the connecting homomorphism, and so lives here. So is multiplication by x. And 3, if x is the regular, we haven't discussed regularity of the complex, but the definition is the same. If multiplication by C is a monomorphism for the complex to itself. So if x is irregular, then tensor product of the Kazoo complex and complex C and quotient of the complex by the subcomplex xc are quasi-isomorphic.
What is C dot regular?
I just said this in words. You still can consider multiplication by x on the complex.
Yeah.
It's a map of complexes.
Oh.
I require this map to be monomorphism in the category of complexes.
Yeah, I understand why I have a problem with this -1 because I usually work over homologies and then it
Yeah.
should be-
But in homology, you can, I think you can do a different convention. So let's see.
Yeah,
We'll see this during the proof. Well, the proof will be just the attempt to explicitly understand what is this tensor product of the Kazoo complex and some complex C. So let's do this. So take a Kazoo complex on one element, take a tensor product with some other complex, and in the degree m of the tensor product, well, we by definition have a direct sum, I plus j is equal to m, then we need to take in the Kazoo complex part of the degree I, take a tensor product with the part of the degree j in the second complex. So, but here we can notice that if we just write this Kazoo complex for one element, this is a very simple complex that looks like this. Right? You have ring in degree 0, you have ring in degree 1, and the map is just multiplication by x. So then, well, essentially, when we look at this sum over all I plus j is equal to n, the possibilities for the I, this would be only 0 or 1, right? So, and this complex, when I is equal to 0, this is ring, when I is equal to 1, this is ring. So essentially this whole sum is just the sum of two things. This is Cn plus Cn minus 1. Right? Just as a graded thing. Okay, now the differential. Well, the differential on the tensor product, let me again call dn. This is on the Ri tensor Cj. So here, of course, I assume that I plus j is equal to n. And this is just elements. So Ri is from the first complex of degree I, Cj is from the second complex of degree j. So by definition, differential on the tensor product is the following. I need to take di for the first complex. I'm going to call this dk to indicate Kazoo. So this applies to Ri. Take a tensor product with Cj plus minus 1 to the I, Ri d. So now this is differential of the complex C. So I'm going to write dc with the index j, Cj. Okay. That's a standard definition of what is tensor product. So what's the differential on the tensor product of two complexes. But with the differential in the Kazoo case is quite simple. Let me write this as two cases. So dik, this is 0 if I is equal to 0. And this is multiplication on x and I, but I is equal to 1. Right? I'm just rewriting this the same thing that we have a complex here, just exactly the same definition. Now I can plug in this formula into this formula and write cases for the differential dn on the tensor product. Okay, so differential dn on the Ri tensor Cj. So this is R0 tensor dn Cn. This is when I is equal to 0. And this is x R1 tensor Cn minus 1 minus R1 tensor dCn minus okay, minus R1 tensor dCn minus 1 applied to Cn minus 1. Okay. Check this. This is just the same formula as before, just divided into cases according to the Kazoo differential. But of course, if you look here, this differential on the C is a R linear differential, right? So this is tensor product over R, so we can just as well forget about this tensor product and move this R0 here, right? When we identify this with the Cn. So I'm saying that if I want to write the matrix, so the differential dn from the Cn plus Cn minus 1 to the Cn minus 1 plus Cn minus 2. So I want to write a 2 by 2 matrix. So as matrix, well, this line just give me a differential on the C, and I don't do anything on the second summand, right? So this is 0. And for the second line, I can as a matrix write this multiplication on x, and then we have minus, so minus d n minus 1c. Okay, this is the end of the computation. Okay, questions?
Почему d0 это 0, а d1 это x? Разве не наоборот?
Well, let's see. So the map was supposed to, the Kazoo complex is a map of degree -1, right? So if I want this to sit in degree 0, and I definitely want this to be in degree 0, then I need to put this into the degree 1, right? So this is living in degree 0, and this is living in degree 1. Then the differential, which is just multiplication of x, is a differential of degree -1. It's decreasing by 1. But now I see that if I have degree 1, which is element here, then the differential is exactly what it's doing, is multiplying by x. And in degree 0, well, I just don't do anything, I map everything to the 0. So I think this is correct.
Okay.
Okay. And actually, with this computation, we proved one. That is because a cone, so cone, let's say this is a remark for those of you who haven't seen cones before, that if you have one complex, C, say, and D, right? And you have a map from C to D. You can say that the cone of this F is a new complex which is obtained as the, you need to take, well, if you want to take this in degree n, then you take C in degree n plus you shift and you take D in degree n minus 1. And then the differential on the cone, say D C of F. This is precisely by definition given by the 2 by 2 matrix. Well, I can write this as a 2 by 2 matrix because it has this direct sum of two things. And this will be differential on the C, this will be differential on the D, but with -1. And -1 is coming because I shifted this complex. When I shift the complex, I'm supposed to change the sign of the differential. So this is the reason for this -1. 0 here in my convention, and here you'll get just multiplication action on F. This is just a definition of any cone for any two complexes and any map between complexes. So what we actually see by this computation, that we precisely, by doing this computation, get the cone. It's the right complex with the right differential. Yeah, and so the motivation for the cones, if you took the algebraic topology, the motivation I think is the following. You take two nice topological spaces, you consider chain complexes that compute, say, singular homology, right? And have a map between spaces, a map between the chain complexes that compute the singular homology, and then you can kind of glue along this map x to the y, and you want to ask what would be the resulting homology. Well, if you do this on the level of complexes, the construction is this cone. So that's the motivation why we call this cone.
Как мы действуем на dn-1 f вот в этой матрице?
Не, мы на CN действуем. На CN.
Wait, no, I think he's right. Yeah, so
Строчку
it-
матрица от того, что мы умножаем.
Yeah,
Строчку умножаем, или
it-
матрицу
it-
умножаем на столбец.
no, I want action, of course, on this side, right? I want something from this C and want something from the D, right? That's how I usually multiply matrices and rows. But if I do this, right, I guess if I want this definition to be correct, I need this to switch the order of the C and D. Maybe like this. Then this is from the D to C, so this, now this I think makes sense.
Yeah, by differential we get lower index, like differential from Cn to Cn minus 1. Yeah. Then it's correct.
Yeah, so yeah, this everything is the chain complexes.
No, we will have differential from Cn to Cn plus 1 because
No.
when we apply f to Cn, we have element of Dn.
No, we
It's-
apply f to Dn.
Ah,
Now we're doing like that.
okay. We change, I
Yeah.
get. Well, now it's correct.
Yeah, I think what we have now is correct. Well, anyway, so how much?
Like 5 minutes.
Yeah, 5 minutes. Okay, but because that's the only thing I want to prove in this proposition, because I want to say that part 2, you just go back to your homological algebra, look at the definition of the connecting homomorphism, and doing explicit computation and see the connecting homomorphism multiplication of x. It's quite a long and annoying computation. I don't want to do this on the whiteboard. Now, and the part 3, this follows immediately if you know this general property that whenever monomorphism of two complexes, you compute the cone for the monomorphism, then this is exactly this is quasi-isomorphic to the quotient of this, to the cohort of this monomorphism. I left this as an exercise in the first assignment. I think it's a nice thing to know from homological algebra, nice thing of the cone. So if you know this general property, this 3 you don't need to prove, it follows immediately.
Can you repeat what is general property?
The general property, you can find it in the first assignment. It will be something like this. You have, say, C prime. This is a subcomplex inside C, right? So say this is embedding. And then there is quasi-isomorphism between the cone of this embedding and the quotient. Of course, quite clearly, the complexes are not isomorphic, but they are quasi-isomorphic.
Can you please explain why we have exact sequence in the second statement? Yes.
Well, as I was saying, that would be always true if you just if you just go to the definition, or go back to the definition of the cone, right? And with this definition, for example, you can see that you can always embed C into the cone of F, right? Just as a direct summand. And then, of course, you can always project again on the second direct summand to the D, but you need to shift this by -1, because this is Dn minus 1. So without differentials, this is clear. And you can check immediately just the computationalist matrices that for if you look at the commutative squares, that everything commutes.
Будь осторожен, когда -1, там дифференциал с минусом идет.
Yeah.
As it's supposed to be, because the shift by 1 in the complex is supposed to change the sign of the differential.
Sorry, извините за мою необразованность, а почему в стандартном определении дифференциально-тензорного произведения комплексов возникает минус?
Well, I would say that this is a standard Kazoo sign convention, meaning that whenever you have two graded elements and you switch the order of these two elements, you're supposed to multiply by the -1 to the degree of one element, degree of the other element. That this is what all possible graded elements. Here we have a map, and here we have an element, right? So whenever I apply D to the C, I kind of switch them around, this Ri and the D. So D has degree -1, so it's not important. So what's important is just the degree of this element, hence this additional sign.
То есть, если это не сделать, то не будет комплекс в итоге. We should put the sign.
Well,
Так дифференциал в этом в комплексе Кашури определяется, но если мы его сюда не применим, мне кажется, там какие-то проблемы.
Нет, просто...
Yeah, I want to say that there are some problems with. I've gotten through those problems, I think, several times. That in different texts there are different conventions, and I think somehow you can maybe you can survive if you just erase the sign. The question is, of course, is it correct that the square of the differential is 0? Can you do this without the sign? So I think this is the exercise that you can check. With the sign it works.
Без минуса вот там.
Ну понятно, что это будет не конус тогда, да?
Yeah, and also mostly for this course I'm using the book by Bruce and Herzog, one of the two books I recommended, and they kind of do a computation when they switch around, they compute the tensor product of the C and the Kazoo complex in the other order, and then they don't see the cone. They see construction that's like a cone. For example, there is no sign here, but there is something like -1 to the I -1, so additional sign here. So up to a sign it is a cone, but if you just switch the order in the other way, you can immediately see this is a cone. Okay, I think now it's time for a break.
Кстати, трансляция запустилась. Вот там с 50 минут на задержке.
50 минут?
Ну,
Тоже видите, как вам сегодня повезло. Сегодня трансляция такая не полная, и сегодня вы пришли.
Да, вот я как раз хотел спросить, мне пришлось пропустить это занятие. Я вот не очень понял, в прошлой лекции вы объясняли то, что было выпущено во второй.
Ага.
Вот, и там было, что у нас есть морфизм.
Да, но там два свободных модуля, и мы можем доказать, что если кому привести к новому максимальному делу, то это произведение сказать, уже инициирует.
Да, вот у меня вопрос, почему, если есть такой изоморфизм, почему из него вытекаем следует, что не изоморф? Вот у нас...
Если у вас вот это изоморфизм, если у вас есть два модуля, не имеет отображения, вы приводите к модулю максимального изъява, например, мы с вами говорим на произведение, то именно поэтому это очевидно изоморфизм, потому что то говорит, что у нас какое-то ядро. Да?
Да, вот.
Берете какое-то ядро, и видите,
Сейчас можно ручки? Просто вот у нас есть, допустим, мы знаем, что это изоморфизм. Здесь есть какое-то ядро. И когда мы тензорно умножим, здесь будет ядро тензорно К ложится сюда. Но здесь уже не обязательно будет точка.
не обязательно, нужно еще знать, что МН свободный модуль. Сейчас что можно здесь сейчас происходит? Отображение.
Ну, Аня, мы же...
На образ. Вроде на образ, да? То есть я образ пока не знаю, что мы должны увидеть.
А если бы они были свободными, здесь бы обязательно ноль был, просто даже не точно наследуется?
Ну, это тоже, да, если примерно точно.
То есть, ну, если бы субъективно, то, короче, точно свободно.
Сейчас, во-первых, точность как бы то, что чем мы занимаемся, мы знаем, точно справа, потому что когда проблема, когда мы рассматриваем, что это информативно. Здесь просто я много
Да, но непонятно почему. Просто у нас может быть вот такой морфизм, типа из m фактор по максимальному идеалу. это изоморфизм, если мы фиксируем по максимальному идеалу, то станет изоморфизм. Но это не изоморфизм.
Чем поймешь?
Мне казалось, что всего уже хватает, но просто сейчас понять, как это правильно сказать.
Наверное, тут важно, что это подмодуль свободного образ.
Ну, в любом случае, в этой ситуации здесь у нас будет все-таки точность справа. Да?
Хорошо.
Значит, на самом деле, если мы здесь начнем дальше писать, нам надо писать что-то типа Тор-1, что, соответственно, n. То есть здесь мы знаем, что у нас это будет изоморфизм. Да? Значит, у нас получается, что у нас изоморфизм здесь.
Здесь дальше будет.
Но нам потому что Тор-1 между яблоко, а n свободен. Поэтому такое считаю, что именно последовательность с изоморфизмом здесь. Да? Ничего, я почему-то решил, что это просто очевидно. То есть у нас есть сюррективное окружение, следствие, мы умножаем на получаем изоморфизм, то мы должны быть изоморфизмом.
Это кажется, что это как-то похоже на левый напрям, но вот вроде это неверный факт.
Нужно очень еще одну задачу. Что у нас там еще будет возможно?
Ну, у нас просто есть, по сути, все, что мы знаем, то, что этот образ фи, это подмодуль свободный. Причем такое, что будет сохранять сингулярность, когда мы на можем.
Вот это надо написать, что у нас есть образ фи, мы можем в там будет какой-то еще фактор. После этого мы назовем это дело умножаем на фи, да? Получается, будет тоже. Тоже между фи и двумя.
По-хорошему, чтобы тоже между принципами
Может быть разрешенный, просто то, что последовательность надо говорить и я. Точнее, да. И, так,
И нужно явно использовать как-то, что уже свободно, пока это никак не использовать.
Задачу можно взять, дополнить вот, f каким-то свободным модулем, чтобы на g был эпиморфизм после тензорного умножения на k. Тогда это полимен Каям сам изоморфизм, а потом тор уже g будет равен нулю. И поэтому это будет мономорфизм, тоже полимен Каям.
Сейчас. То есть у нас есть вот отображение.
Есть отображение из f в g, φ. Оно после тензорного умножения на k становится вложением. Можно взять к f прибавить r в какой-то степени, так, чтобы после тензорного умножения на k это был изоморфизм. Полимен Каям — это селективное отображение, потому что коядро после тензорного умножения на k становится нулем. А дальше мы имеем селективное отображение, рассматриваем его ядро, умножаем тензор на все на k и получаем точную последовательность, потому что образ, свободный модуль g, он плоский. Там тор будет равен нулю. И поэтому k нуль.
Сейчас мы как раз про это и думаем, почему образ плоский.
Потому что мы дополнили не образ плоский, образ g будет весь. Я дополнил f. Так
Это
что...
такой непростой аргумент. Мне казалось, что здесь как-то...
А почему еще раз образ плоский?
Потому что мы дополнили f с каким-то свободным модулем так, прибавили к нему прямое слагаемое так, чтобы образ был g.
Нужно подумать.
Ну, могу ли это хорошая задача вернуться к этому на семинар на следующей неделе. Okay, so this derived one corollary from this proposition. So suppose we have a sequence of elements in the bracket R, and M is an R module. So first, if we consider a sequence x prime, which have all the elements bar the last one. So then there is a long-exact sequence of the Kosovo homology. So here we have hi x prime m. Then this is mapped to the hi x m, and then to the hi minus 1 x prime m. Yeah, and by the term. So the last term, so this will be just multiplication of x,
and this is hi minus 1 x prime. Yeah, so of course I don't really need to prove this because this is just the previous proposition where I take as a complex C, Kazoo complex for this sequence, x prime. And then use the, I think, part 2 of the proposition, yeah, for the long exact sequence, and I'll get this long exact sequence. So this immediately follows as a special case of proposition. For the second part, I choose some p, which is less or equal than n, and I can split this given sequence into two sequences. I'll have x prime, which is sequence of elements up to xp, and then I have x double prime, which starts with the p plus 1 and then continues up to xn. So take this splitting, and if we have this and this sequence x prime is weakly M regular, so then we have the following isomorphism. We can compute Kazoo homology for the sequence x and modulo M, and this will be isomorphic to the Kazoo homology for this truncated sequence x double prime, and the module is the quotient of the by the submodule x prime L. Well, this kind of a little bit of formal notation, but I hope this is clear. I take this sequence from x1 to xp, I generate an ideal by this sequence, and this is just the product of this ideal and M, this gives me submodule, so I can take a quotient by this submodule. Okay. Proof. So, as I was saying that for one, apply proposition for the complex C being just the Kazoo complex on the x prime. Now 2 is actually requires some proof. Now I take complex C to be the Kazoo complex on the sequence x double prime. Okay, so this is the complex. I don't use induction. So by induction, it is enough to take p equal to 1. So then we have short exact sequence M. So what's this weekly regular? X double prime. So I think we have x1, M, and then the quotient. Wait. I'm assuming that x prime is weekly regular. So x1 is weakly irregular, so this is not xn, this has to be x1. So this is x1, and this is also x1. So this is x1 and x1. Okay, so we have short exact sequence of modules. This produces the short exact sequence of Kazoo complexes. So we have K, x double prime M, So here is the map induced by the multiplication on x1. Then we have Kazoo complex for the x double prime m. And finally, we have Kazoo complex x double prime and the quotient module. Okay, so yeah, so by looking at this computation, just at this short exact sequence, we can see that this is the complex for everything except x1, right? Now here I take a quotient. So essentially, when I consider this thing, this is a quotient of this Kazoo complex by the x1 Kazoo complex on the x double prime. And we know that this quotient is isomorphic to the Kazoo complex, to the tensor product of this Kazoo complex and the Kazoo complex on the one element. So I'm just using what I know from the previous proposition, that if I take this quotient, right, this is quasi-isomorphic to the tensor product on the x1 and this Kazoo complex double prime. Right, so this is my previous proposition. But this is, of course, by the kind of property of the tensor product of Kazoo complexes, we can identify with the Kazoo complex for just x. So we see that the Kazoo complex for the sequence x is quasi-isomorphic to this quotient, which we already identified with this complex. And this gives us precisely this isomorphism. So I want to say that it will use the second property. So in particular, we have the following corollary. So that the hi for the sequence x with coefficients in the module m is 0. And this is for I greater than n minus p. Okay, can you tell me why?
We're still working when P is...
Yeah, the same assumptions as in the corollary. Well, this is just kind of not even really corollary, just a remark to this corollary.
Because length of Kazoo complex for x prime prime is
Yeah,
minus p.
exactly. Because now we're computing this thing, we reduce this computation to this thing, but this is by construction has the length, as you say, which is less than n minus p.
Can you repeat
This?
this? Yes.
Yeah, well, we try to compute this homology, and we can compute by using this isomorphism, this homology, right? But this is homology for the x double prime, which is a sequence of the length n minus p. So by construction of the Kazoo complex, there is nothing in the degree greater than n minus p, just 0. So not just homology, but there is nothing in the complex. Okay. So theorem. So we have, as before, M is an R module. We have a sequence X. So a sequence in the ring R. And I said I to be the ideal generated by this sequence. So if I contains a weak M sequence, let's call this sequence Y. So length of this sequence is M. So then we have the following two observations. HI for the sequence X and the module M is 0. And this is for all indices I which are greater than n minus m. And H with the index n minus m is isomorphic to the home R modulo I m quotient by the y m. Again, take an ideal generated by the sequence y and take the product of the ideal and the module. So of course we know that this thing we can identify with the x with the index m between Ri and m. We've done this computation before, so this is not really a new part. Okay, proof. So the proof will be by induction on m. Okay, so based on the induction, m is equal to 0. So there is no a weak m sequence. Well, then there is no really a statement here, right, for the vanishing. The only thing that we need to check is that the top homology are exactly as I described them, which is not very hard to do. We just look at the end of the Kazoo complex. We'll get some top homology. So let's just write that this is top homology. This is the kernel of the map, so I have top exterior power tensor m. Now here I have the differential, which is just Kazoo differential tensor identity on m to the lambda to the n minus 1 Rn tensor m. Well, there's something else in the lower degrees, but we can see that the top homology, by definition, well, first of all, clearly this thing can be just identified with the module m. So top homology is just some submodule in the m. So this will be elements, say t, in the module m, such that, well, the differential of this t has to be 0. But I claim that this condition that the differential has to be 0 can be written in the following way. It is 0. Right? So I is an ideal generated by all these x's. So this d is essentially what it's doing is just multiplying by each of these x's and give you an element in this exterior power, which can be identified with the Rn times m. So if the differential is 0, it means that any generator of the ideal I is 0 when multiplied on t. So clearly I can write it like this. But then this can be of course identified with the home over R from the R modulo I to the, in this case just M. There is no sequence Y. Right? So this identification is completely standard. If you want to define such home, you need to say where class of 1 is going, and the class of 1 is going to the element T. Okay, so this finishes the situation when m is equal to 0. Now, for m positive, I look at the short exact sequence with y1, which I assume to be regular. And for shortness, let's just say that the m bar is the quotient of the m by the y1m. Okay, For this short exact sequence, well, we'll get the corresponding short exact sequence of causal complexes, and then we can look at the long exact sequence of homology. This is what we get. We'll get hi x m. So here we have multiplication by y1. Here we'll have hi x m. Then hi x m bar, hi minus 1 x m, and then everything repeats with the shift index. Okay. So this is the long exact sequence that you get, and now what we can notice is that y1, as we discussed in the beginning of the lecture, is in the annihilator of all the causal homology as an element in the ATM. Hence, this long exact sequence of homology actually splits into short exact sequences. So we'll get 0 hi x m, then we have hi x m bar, and the last term is hi minus 1 x m. Okay. So the vanishing condition that we have here immediately follows from these short exact sequences. We just do this step by step by looking at the short exact sequences and get everything vanishes. So this is clearly done by induction. So the only thing that is maybe requires additional little proof is that the computation for the hn minus m. For this I write the same short exact sequence of homology, but for a specific index. So this will be h with the index n minus m plus 1, x, m, then it will be h n minus m plus 1, x, and 1, and this is h n minus m, x, m.
Can you repeat how did you use the first property?
What was the first one?
The vanishing of larger, like I larger than m minus m.
Well, by induction, but by induction. So we assume that you know this vanishing, for example, for m equals to 1, right? You want to get this vanishing for m equal to 2. So then here you'll get the vanishing, right? Because this is the m bar. Now you take a portion by the first element, so this has a length
Smaller by 1.
Smaller by 1. And for this thing, you'll get the vanishing, right? So get the vanishing. So this is the vanishing in the causal homology, but not from the degree 0, but from the top degree.
Mm-hmm.
So you already have this vanishing, but if you have this vanishing here in the middle, this is 0.
Yeah, then both of them should be 0.
Yeah. So this is a quite simple induction. This is also quite simple induction, but maybe a little bit less simple. Let's look at this short exact sequence. Now, what we have here, I claim that this is 0, right? No, because this has this plus 1. So this is 0. So the conclusion is that the h with the index n minus m for the sequence x and the module m is isomorphic to the form r modulo I. Now I have m bar and the motion by the sequence y starting with 2 up to ym. Okay. because this is 0, since I have isomorphism of those two things. Now I'm computing this, I'm using this thing, but I already know the answer for this thing. And so this is by the inductive step. So I know that this is of this form, but the sequence starts with true.
Why it is 0?
Why does the sequence start with 2?
Well, because this is m bar, right? So m bar is when I take a quotient by the y1. So the weakly regular sequence that we have for the module m bar is y2 up to yn. Yeah, and this thing is 0 by the induction hypothesis.
Мы для m доказываем. Мы доказываем утверждение для m, хотим.
Yeah, we're proving this theorem, so I'm saying that vanishing I already know.
То есть мы для всех m доказали зануление.
Yeah, and I'm just trying to prove that this top homology, well, the homology with the index n minus m is also have a correct answer, right? So this I have because I already have vanishing.
Это когда мы доказали.
But by this computation. So we first prove the vanishing, right? And then we will kind of analyze the structure of the first non-vanishing term when you count from the left. I think it's useful to imagine in your head how homogeneous the Kazoo complex lives. So we have a lot of vanishing when you go from the left, right, from the top degree. Then there is a situation n minus m where you have the situation where you have first non-zero homology, and then there's something else. Yeah, so this vanishing we have because we prove vanishing, and this lives not in the n minus m, but this is one step to the left where we already have vanishing. So this is 0. So in other words, I, which is n minus m plus 1, is greater than n minus m. Yeah. So this is why we have vanishing. Okay, so this is 0, I have this isomorphism, I'm still trying to compute this, and now I know that this will be the first non-zero Kazoo homology from the left, but for the module m bar. And by the induction hypothesis, I already know how these things are supposed to look. They're supposed to look like this. For the m bar, and then on the m bar, I have regular sequence which has length m minus 1 and starts with y2. So now what I need to do is just identify this module with the module that I want. I want m, y, m. And this thing, well, this is the third isomorphic theorem for the modules, where I can take quotient in steps. So I can take quotient first by half. I guess it's not very hard to see. Okay. Yeah, so this is the end of the proof. And as I was saying, this part I don't need to show because we've done this computation before. So this is just a reminder of what we already know. Okay. Okay, so I have another theorem, and there is step by step trying to analyze how Kazoo complexes are related to the notion of depth and regular sequences. So the next step is the theorem okay, so R is an Arthusian ring. R is an Arthusian ring. M is a finite R module. As before, I have some sequence. So X is a sequence. And I have an ideal, which is just an ideal generated by the sequence. So then I have the following properties. So first, all homology for the Kazoo complex are vanishing if and only if m is equal to the Im. True. So if there is index I, of course this is index for the causal homology, so this is between 0 and n, such that hi x m is not 0, then the depth with respect to the ideal I of the module M is equal to the n minus the supremum of the I such that hi of x m is not equal to 0.
Yeah, in the first one, I standing for what?
I standing for any index between 0 and n. Maybe I need to correct this. So if there are no homology at all, so for I, then this is equivalent to m is equal to Im. Okay. Well, the first case is kind of trivial case. It's just for completeness, but the interesting statement is, of course, this second statement, right? So to be on the safe side, I'm formulating that I have a situation where I have at least one non-zero causal homology. Then I can see that the depth is related to the causal homology, and the relation is given by this formula, and you can interpret this that the depth, this depth, is showing how many zero terms you have in the causal complex starting from the left. Right? So how many vanishing from the left you have. For example, you have a regular sequence, then you have vanishing, right? So this depth is equal to the n, right? So then you have vanishing of everything except the h0, and h0 is just m modulo Im, so this will be a free resolution m modulo Im, yes. Okay.
What will be a free resolution?
The causal complex with coefficients in m. Right, so if x is a regular sequence on the modulo M.
It's free resolution of m modulo Im.
Well,
I suppose it's free resolution for r modulo I, it's true.
yeah, you're completely correct. This is of course a free resolution for R modulo I. This makes sense because the terms in the causal complex will be free modules. But well, if you take a tensor product with M, well, this is just some acyclic complex for which we know the zero homology. So it's not really free resolution. Sorry. Okay. So proof for one. This is if and only if statement. I think one direction is completely clear, right? Suppose we have all this vanishing of the causal homology. Well, in particular, we have h0, right? Which is supposed to be 0, but we can explicitly compute h0. There's always this quotient. The end of the proof. Now, in the other direction, I take a prime ideal P in the spec of the ring. Now, let's take the causal homology.
Можно еще раз, как первое получилось?
Well, we've only done this in one direction. If I assume this, in particular, I know that h0 is 0,
Yes.
but h0 is this thing.
Окей.
So this is h0. Okay, so in the other direction, I know that m is equal to the Im. I want to show the vanishing of all causal homology. So I take the causal homology and localize this as a prime ideal. So if I can show that all such localizations for all primes are 0, then I'm done. Well, first of all, let me write this formula and then I'll ask you why this is true. So if I localize the Kazoo homology, I'll get the homology for the localization. Do you see why we have such an isomorphism?
Well, because localization is flat.
Localization is of course flat. Well, it preserves, for example, yeah, it's an exact function, so it preserves homology. So we'll get this. Okay. Now I need to consider two cases. First case, if I is not contained in P. So then I immediately claim that the HI X MP is 0 for any I. Question is why? You can immediately see that all these homology are 0.
Well, then
Well, we actually already know one situation and we can immediately say that all the homology are 0.
Because subjective. No?
when I is equal to whole ring,
Yeah.
and that's this is
Yeah, if I is not sitting inside P, then what happens if I localize this prime ideal at P? I'll get just the ring, right? Because I have some invertible elements in the ideal.
But we know exactness in... Ну, в обычном комплексе Кожуля мы же еще на MP домножаем тензорно.
No,
у нас вообще для всех комплексов.
that's not a problem. Because we proved that if you multiply by any element in the ideal, then this is homotopic to 0. And if you multiply by any module, this is still homotopic to 0 because you can apply apply tensor product with M to the homotopy maps. So I was saying that on all four Kazoo complex, this is homotopic to 0. So and then in a special case, when the ideal is just a ring, 1 is homotopic to 0. So this is constructible complex and has trivial homology.
Что значит стягиваемый комплекс?
This is by definition means that the 1 on the complex is homotopic to the 0.
Yes.
Well, it's just a cyclic complex.
No.
No.
No. If this is homotopic, this is definitely acyclic. If this is acyclic, it might not necessarily homotopic. It's kind of the difference between homotopic category and the derived category. Okay, so we finished this proof only in one case. Now, of course, we have another case. Now, if I is not I is not contained in P was the previous case. I is contained in P. Right? But if I is contained in P, then I can look at this condition, M is equal to the IM, and then if I localize this, I'll get the condition that MP is equal to the IPMP. Right? But I have a finite module. And this IP clearly sits inside the radical, which is just the maximal ideal. So not just the homology is 0, but the whole module is 0 by Nakayama Akizuki group. Well, and anyway, if the module is 0, there are no homology. And this finishes the proof in the other direction. Okay, finally, this formula. So let y be a sequence, say y1 up to yg. So inside ideal I. This is a maximal M sequence. So then by the previous theorem, right, we know that we have the following, that there is a vanishing of the HI for the I greater than n minus g, and homology with the index n minus g can be identified with the Hom R modulo I M modulo Y. Which is not equal to 0. Well, forgive me for doing this, but this is not 0 by what we proved in section 1.2. So this, I even have a notes for myself. I need to say that this is the first theorem in the section 1.2. Then
The section about it, yeah.
yeah. So this is non-zero, and we have this. This is precisely the proof of the second statement. Okay, so this is probably the most important property of the Kazoo complex, meaning the dense sensitivity. So the number of zero homology in the Kazoo complex counting from the left is precisely the depth of the sequence. So precisely the depth of the ideal on the module M. Okay. I have one lemma which is, well, at the moment probably won't be clear why I need this lemma, but I will use it to prove next theorem. So even more special case, I have local Noetherian ring. I find that our module a sequence, as usual, and the maximal ideal, of course. And I have this kind of truncated sequence, x prime. This is all the elements, but the last one is xn minus 1, so I just draw the last element. So then I have the following claim. If I know the vanishing for the Kazoo homology for the sequence x, some module m, then I can have, I can say that there is a vanishing for the Kazoo homology for the x prime sequence and the module m. So if I drop an element from the sequence, the vanishing is preserved. The proof is relatively straightforward. You just need to, again, write the long exact sequence for the Kazoo homology that I was already using, I think, at least once, maybe even twice. And all these sequences, it's important to write the correct sequence. So correct prime where it's supposed to be, and not right where it's not supposed to be. Okay, yeah, so that is the sequence. Now, so what we have? So we have, it is given that this is 0. Right? But then it means that this multiplication on the xn as an endomorphism of this module, which is a homology, Kazoo homology with index I. This is an epimorphism, so I can write hi.
Какая короткая точная последовательность, соответствующая это? Откуда мы взяли эту?
Well, this is still the same short exact sequence of complexes that we first prove this for some complex C, and then we specify this to some situation where C is a Kazoo complex. Now in this case, C is a Kazoo complex for this sequence, and then you have a Kazoo complex for the x prime in the beginning, then you have Kazoo complex for the x, for the whole sequence in the middle, and then you have the same Kazoo complex but shifted by -1. That's that one. We actually have only one long sequence of complexes in this case. Well, we have kind of this in general for any C, but how we usually use it, if we just take C to be a Kazoo complex to a smaller number of the elements in the sequence. Okay, so it is given to us that this is vanishing, and then I can say that hi x prime m is equal to the xn hi x prime, right? But this means that hi x prime is 0, right? I have the last implication.
By Nicodemus.
Again, yeah. So this is an ideal. This is inside a radical. So this is by Nakayama. Okay. So just a little technical statement that I'm needing. I need the proof of the next theorem, and the next theorem is quite nice. So we have local Noetherian ring. We have a finite module. Finite R module, some sequence inside maximal ideal. So all the standard assumptions. Ideal I is the ideal generated by this sequence. So then the following four conditions are equivalent. First, depth I m is equal to n. 2. There is a vanishing of the Kazoo homology everywhere in positive degrees. 3. Just kind of summary of what you already know. 3. There is a vanishing
The second one is not connected to n.
I mean, I can write that I is running between 1 and n. It's kind of understood.
Yeah. This is.
Can you repeat, please, what you say about?
Condition 2. Then there's a vanishing of all the Kazoo homology for all indices between 1 and n. I can just as well write greater than 0. Because of course if this is sequence of length n, the homology can only go up to degree n. So condition 3 is less trivial. In condition 3 I require vanishing only for the first homology. And condition 4 is that x is an M sequence. So all these four conditions are equivalent in the settings of the finite modules or local Noetherian rings. Proof. Oh, something we already know, that 1 is equivalent to no. If 1 is equivalent to 2, this is by previous theorem. The theorem that was before this lemma. Now, of course, 2 implies 3 is clear. Now, the only non-trivial implication in this whole proof is that the 3 implies 4. If you know, if you can do this, the rest is again clear. Okay, so for this we need this lemma. Okay, now again I need this the same log exact sequence of the Kazoo homology. Now let me write the first 4 terms. So this will be h1 x m, then there will be h0 x prime m, multiplication by the xn, h0 x prime m, h0 x m, 0.
Там же где-то вот из-за этого сдвига тут как-то это, ну, последние они разве все h0 будут? Или там вот 0 это h-1, да?
Well, the beginning will look like this, well, because what else you can get? There's no h minus 1.
Yeah, that's both. Yeah. Uh-huh.
I'm just writing, if you write this long exact sequence, what would be the first 4 terms that you'll see? You'll see these 4 terms. Okay. So what we have, the assumption is that h1 xm is 0, right? So this is 0. But if this is 0, it means that multiplication on the xn is monomorphism, or in other words, xn is regular on the h0 x prime m. But of course this we can explicitly compute. Zeros Kazoo homology are easy to compute. This is just quotient of the m by the x prime m. So it's kind of we prove the induction that the xn is regular on the module that we obtained by quotienting by all the previous ones. And by the lemma, h1 x prime m is also 0. So we can continue doing this induction, but for the sequence of the n minus 1 elements. And continue, and get that the sequence is regular. Okay, so this is 3 implies 4, and finally 4 implies 1. I want to say this again clear, right? Because, well, maybe I say a sentence why this is clear. Well, if you know that this is a regular sequence, right? You want to say the depth is n. Well, this whole regular sequence generate the ideal. Right? Clearly, this is maximal. We can't put anything more. So this is a max. So we have a maximal m sequence in the ideal I, and this maximal sequence has an Sn. So that's the depth is equal to m. Okay. So probably in the practical applications, this is what you want to remember from this whole section. That this 4 conditions are current, and this is so surprising that we can, or probably it's surprising, but this h1 is enough. Well, I just want to say that if you drop that this ring is Noetherian, I think even for local situation, the situation is a little bit more complicated. You have regular sequences. If you have a regular sequence, of course, by the general technique, you can prove that in the Kazoo complex there are no high homology. So these sequences are sometimes called Kazoo regular or homologically regular. There are 2 kinds of terms that we can use. So in any situation, without the assumption that the ring is material, there is an implication that regular implies Kazoo regular. Of course, Kazoo regular implies h1 regular for trivial reasons. And in fact, even in a general non-Noetherian situation, h1 regular implies quasi-regular. So the statement from the first lecture that regular implies quasi-regular can be factored into 2 substatements. Regularity implies Kazoo regularity, this implies h1 regularity, and h1 regularity implies quasi-regularity. In the non-Noetherian setting, all 4 conditions are different. There are examples that they are not equivalent. So there is really a paper on this old paper from 72nd. Okay, so this was the end of the first chapter, and I want to start the second chapter now. I was hoping that I can do all this in the first half, and in the second half I'll do Homological things, but it looks like I just start them and continue next time. So chapter 2. Homological modules and rings. This is quite short chapter actually. Much shorter than the first chapter. So, first section, definitions and basic properties. Well, actually, maybe it was too early for the first section. I want to say that in this chapter, I want to assume that all rings are Noetherian, all modules are finitely generated. All modules finitely generated. It's a standard assumption for the standard period. You can discuss what it means to be Cohen-Macaulay non-Noetherian setting, but it's not, well, usually not something that you do in the basic course, but there are still papers that are writing something Cohen-Macaulay in non-Noetherian setting, so it's not a standard theorem. Okay. Well, first observation before I do the first definition. If I look at the dimension of a module, which is finite module, then this is dimension of the ring modulo the annihilator of this module. If you wish, this is definition of the dimension of the module. Now, annihilator of the module is contained in a prime ideal if this prime is associated to the module. But if we have such containment, then clearly we have dimension R modulo prime, which is associated, is bounded above by the dimension of the module. So, for a finite, module M over local Noetherian ring Rm, but R would be enough. We have the following sequence of inequalities. We have depth of M, which is less or equal than the dimension of the R modulo P, which is less or equal than the dimension of the module, which is less or equal than the dimension of the ring. That is for any prime associated to the module. Okay.
Получается, что любой аннулятор содержится в любом ассоциированном начале.
That's логично.
Почему любой аннулятор? Он единственный аннулятор.
No, annihilator is contained in any prime which is associated. Well, if you look at the annihilator, it clearly consists of zero divisors, right?
Yes.
And the set of zero divisors is just the union of all associated primes. I assume that's everything Noetherian and finite, so there are finitely many associated primes. Prime avoidance give you this inclusion.
For some P. Для некоторого простого.
Prime avoidance для них.
Oh yeah, for some P, you're correct. But then I see something like this. What's the radical of the annihilator? Radical of the annihilator is intersection of all the associated primes, right? Hence, it is contained in any prime, in any associated prime. Yeah. Thank you.
Почему глубина M меньше равна, чем размер вестера?
Remember that was a one-line proof of a corollary of the Isherberg's theorem. Yeah, 2 weeks ago. But we proved this in the first chapter. So this is kind of almost trivial observation. I've done it here, and this is of course completely trivial.
Excuse me, can you please repeat about that annihilator is in prime ideals?
Well, radical of the annihilator of M is the intersection of all prime ideals which are associated to M.
General statement. И это есть записка из Commutative.
Yeah, so all I use about the associated primes are those nodes. So you can see that actually when you do a little bit more advanced commutative algebra, what turns out to be quite important is things, of course, like Nakayama lemma, theory of associated primes, prime avoidance, and if you do something a little bit harder, dimension theory. This kind of the key ingredients of the basic commutative algebra theory. Well, sometimes also integral extensions are important, but probably not in this course. Yeah,
Can you repeat what is the last one?
dimension theory. Yeah, so for this reason, I don't really like the ideas of model book because there is no associated primes there, and it's quite useful when you do anything a little bit more advanced than what is done in the idea model book. Okay, so we have this sequence of three inequalities. One of them is not trivial, but we proved this earlier. Two of them are completely trivial. Now, by looking at these three inequalities, for that when you give a definition. So definition that will consist of four parts, really four definitions. Finite modulo M finite modulo M over local material ring Rm is called Cohen-Macaulay. For shortness, I'm going to write just CM. Just standard abbreviation commutative algebra CM always stands for Cohen-Macaulay. So if M is not zero and depth of the M is equal to the dimension of the M, or M is zero. So unfortunately I need to divide this into two parts because I want to say that zero modules Cohen-Macaulay by definition to have a nicer category. So for example, in the category of Cohen-Macaulay modules, I want zero modules. Okay, so the definition is kind of quite nice in the sense that you have kind of two notions of the dimension, just the crude dimension of the module, and then the depth, and you can kind of count this inductively by the how many hypersurfaces you get to factor the zero, and these two notions coincide. Two, the ring itself is called Cohen-Macaulay if it is Cohen-Macaulay as module. As module. 3.
So we only define Cohen-Macaulay models for local Noetherian rings.
I have definition 3.
Ah.
A module M over Noetherian ring R, not necessarily local, is Cohen-Macaulay if its localization is Cohen-Macaulay for any maximal ideal. Spec M for any maximal. In fact, I can require the definition for any prime, but I can also derive this that for maximal would be enough. We'll prove a theorem that the localization at any prime ideal is also Cohen-Macaulay. And finally, 4, just for the completeness. So a finite module M local Noetherian ring is called maximal Cohen-Macaulay. Sometimes people write MCM for maximal Cohen-Macaulay if the depth as maximal as possible. If depth of the M is equal to the dimension of the ring. Okay. Elementary remark immediately from the definition. that M is Cohen-Macaulay if and only if M is maximal Cohen-Macaulay, sorry, say Cohen-Macaulay over the ring R, maximal Cohen-Macaulay over R modulo the annihilator of M. So any Cohen-Macaulay module is actually maximal Cohen-Macaulay if you restrict the support from the ring to the ring module the annihilator.
Yeah, and definition of maximal Cohen-Macaulay over any ring is the same as just
all the localizations has to be maximal Cohen-Macaulay. Okay. Theorem. I'm not sure who first proved this theorem, probably Grothendieck, but this is a very simple observation. If R is a local Noetherian ring, M, say, non-zero Cohen-Macaulay R module, then the dimension of the R modulo P is equal to the dimension of M for any P associated to the M. So in other words, M has no embedded associated primes. If you know some theory of associated primes, you know that there are kind of minimal associated primes, and then there are non-minimal, we call it embedded associated primes. For Cohen-Macaulay situation, that's not possible. Alright? That is because all the dimensions of R modulo P are fixed. Well, if you require that the depths is the same as dimension, then these two inequalities turn into equalities, so clearly you have this property. So the condition is of course doesn't require any proof, but it's important to notice that Cohen-Macaulay modules has this very nice property, non-embedded primes. For example, that would be a way to construct an example, say, of a ring, which is not Cohen-Macaulay. It has to be a ring with embedded primes. But apply the seminar for the next week, so mostly not Cohen-Macaulay stuff, so we'll look at some examples. Okay, so this is first easy theorem. Now, next theorem. Well, usually when you do Cohen-Macaulay stuff, you work locally, and then you say that if you have something non-local, just localize and everything works out somehow. So mostly I'm going to discuss local situation. So we have local Noetherian ring, some non-zero Cohen-Macaulay module, well, because for zero modules everything is trivial. So then I have three statements. First, the depth in the ideal I and the module M is equal to the dimension of the module minus the dimension of the module IM, and this is for any ideal I2. If we take a sequence, say a sequence of the R elements is an M sequence, if and only if dimension of the M module of this sequence equal to the dimension of M. This is really ridiculous property. I think this minus has to be minus r. I don't have this in my notes. Well, if this is an M sequence, and M is any module, then we know that we have this formula. This is one of the statements on the dimension theory. I suppose you know. At least well, for a ring, you can find this in the ideas and Homological or any other book. For a module, you can find this in Musumuru's book, or there is actually an exercise how to reduce the general case of a module to the case of the ring. It's not a hard exercise, you can do it rather quickly. But what's important that if you have polynomial, you can test the sequence being an M sequence kind of numerically. You just need to check this equality, which is a nice property. Usually this is applied not for modules but for the rings or schemes, that if you start with something polynomial, then every time you take a kind of restricted upper surface, you drop your dimension by one. That's a polynomial property.
So it's like for any M, it's only from left to right, and for Cohen-Macaulay it's both.
If you want, yes. 3. The sequence that I introduced before, X. So is an M sequence, if and only if it is a part also system of parameters. Okay.
Yeah?
Definition.
System of parameters.
No, system of parameters, I'm assuming that you know system of parameters. But do you need to brief remind what system of parameters is? Okay. Well, this is a situation of the local Noetherian ring, and then say, not to confuse with axes, let's call them A. So we have AN. This is a system of parameters. This means the following, that if you take a quotient of the R by the ideal generated by this thing, you get something of a finite length, or another word of dimension 0. So kind of this sequence parameterizes everything geometrically up to 0-dimensional piece. Well, the minimal number of parameters is denoted delta of R, and the dimension theory is the really statement that you have two equalities, that the minimal number of parameters is the same as the dimension, the group dimension of the ring, and also this is the same as the d of R, where g of R is defined in terms of the Hilbert-Sumner function. So in other words, the minimal number of parameters is precisely the dimension. Yeah, I think that's all you need to know.
Конечность длины означает, что это Артиново кольцо.
I said that this is the 0 dimension. Okay. So let's prove 1. So the proof is by induction on the depths. By induction on the depth. So let's look at the case when depth is equal to 0. So this is the first case to consider. Well, if the depth is equal to 0, then I consists entirely of 0 divisors. So there is associated prime such that I is contained in this associated prime. Right? So I have kind of what I need to show that in this situation, right, then the dimension of M and the dimension of M modulo IM is the same. In some sense, I want to say this is completely trivial. It's nothing really to prove, because, well, I have this prime, associated prime that contains I, right? And then I can say that the reverse inclusion for the vanishing sets, right? So I give me kind of some subscheme such that it contains one of the components of the support of M, and all the components of the support of M has the same dimension, namely the dimension of the module. So if I restrict to something even larger, at least this contains this component, irreducible component of the support, so it has to be the same or the same dimension. So and now the same geometrical argument, this formulas. So I have this inclusion of the vanishing sets now support of the M modulo IM. Well, I can write this as a support of the R modulo I tensor M, and whenever we have a tensor product of modules, the support of tensor product is intersection of the supports. So support of the R modulo I is just vanishing set of I. So this is vanishing set of I intersect the support of M. Okay, but well, we know that the V of P intersect the support of M is contained in this support, right? Because V of P is contained in the V of I. But on the other hand, the support of M, we explicitly know that this is the union of the V of P, where P is the minimal associated prime, but this is for a Fourier situation. Every associated prime is minimal. So what we have on in this intersection is just some V of P or some associated prime P. So the conclusion is that there is P associated to the M such that the V of P is contained in the support of M. Hence, the dimension, in the support of M modulo IM. Hence, the dimension of the M modulo IM is at least the dimension of the V of P, which is the dimension of the module. Right. This is what I was trying to say in terms of words. Geometrically, this is absolutely clear. But of course, the reverse inequality is trivial. If you restrict M to some subscheme, well, that is no dimension of the IM less or equal than the dimension M. This is clear by trivial reasons. So the dimensions are the same if the depth is equal to 0. So we have the base of the induction.
Can you please repeat geometrical?
Well, geometrically, I'm saying that I have this M. I'm thinking about this as a coherent sheaf, right? And then it is supported on something, but the something has irreducible components which are V of the minimal prime associated primes. So in this case, it's just all associated primes. They're all minimal for Commutative situation. So this thing is, I take this coherent sheaf and restrict this to the subscheme given by the ideal I, right? But when I restrict this, I still have inside this vanishing set of I, so this subscheme defined by I, and this subscheme which is just an irreducible component of the support. So it means that the dimension cannot drop. That's true. And so of course it can increase, so the dimension stays the same.
What is geometric meaning of depth?
No, that I was trying to say when I was giving the definition. The depth is again counting the dimension, but in a different way. It is count the dimension inductively by saying how many hypersurfaces you need to use to cut to the 0. That's what this regular sequence is. If you have a regular element, that's a hypersurface. If you have a regular sequence of length 2, you restrict to a hypersurface, and you still then again restrict to a hypersurface. when we do this kind of one way, just using the standard dimension, full dimension, and the other way, step by step, by restricting to hypersurfaces, they coincide. This is Cohen-Macaulay situation. Okay, but I really want to finish this proof. The proof is quite simple, actually. We've done the hardest part. So for the depth 0, this is clear. Now, a situation where the depth is positive. So if the depth is positive, we choose x in the ideal I, which is regular on M. And then we just observe that the depth for I and M modulo xm, well, this is more or less clearly from the definition, depth Im minus 1, dimension of the M modulo xm is equal to the dimension of M minus 1, something that you're supposed to know from the dimension theory. And so you see that in this formula, the left-hand side and the right-hand side, when you take a quotient by regular element, they drop by 1. And the dimension, of course, of the M modulo Im stays the same as the same. So the dimension of the M modulo xm, and then again modulo I M modulo xm. This is, of course, the same as the dimension. Oh, this is the quotient is the same. If you take a quotient first by one element in the ideal, you still need to take the same quotient by the Im. Okay, this is the end of the proof of 1. Now 2. Okay, so now I use this last statement from the first chapter. So that the sequence is M regular if and only if the depth for the ideal generated by this sequence is equal to R. This R is the length of this sequence. Right. So this is a statement from the end of the first chapter. Now, now we just use one.
The first one.
Yeah. Yeah, that's the whole proof.
Okay.
3. This is a restatement of 2. And hence this is the end of the proof. Right? Well, because how this is a system of parameters, well, in the system of parameters, we're supposed to get a system such that if you take a quotient by this, you'll get something 0-dimensional. Right? But here we have the system, when we take a quotient by this thing, we drop the dimension as much as possible. So we just find some element which is not in this regular system, etc. So this is really a tautological statement. Okay, so that's it for today.
Can you repeat why dimension of... Почему размерность?
M фактор по xm это размерность m минус 1.
This one.
Yeah.
This is you're supposed to know. This is one of the statements.
Да, это
Второе упражнение.
то, что мы обсуждали, да.
At least I hope you know this for rings, and you can derive this for modules. What is the dimension of the modules defined in dimension? Because that shouldn't be very hard. Okay. So next time we'll continue exploring homological and we'll proceed on homological.
Да, для нас сначала еще содержится, не содержится.
Сейчас будет больше, если я записываю службу, потому что я записываю почему-то. Это казахский
Слушай, как тебя зовут? Ты то, что говорил, когда мы обсуждали перерывы, это какой-то общеизвестная вещь, или сам понял, когда
Нет, я сам придумал.
ты просто когда лекцию смотрел?
Нет, не тогда лекцию, потом думал над этим как-то сделать.
Ясно. А ты понял, почему там прямым слагаемым выделяется?
Да, вот это написать здесь. Где-нибудь. Здесь. Просто нужно. У нас есть щи, потом на х, если мы перейдем, то здесь будет. Это векторное пространство над х, это векторное пространство над х, это вложение. Поэтому здесь можно прибавить х в какой-то степени, там, r, чтобы вот это все было, ну и построить это вложение сюда, так, чтобы это было изоморфизм. То есть получится, что f плюс f в степени r на k. Изоморфизм g на k. Ну, для векторного пространства это можно сделать. Это просто конечномерное векторное пространство. Это просто дополнение существует. Что можно рассмотреть такое? Ну, полим минокаям, если здесь есть какое-то к-ядро, здесь какое-то пси, какое-то к-ядро, я умножу на k, тензорно, оно попадет. Поэтому полим минокаям это 0. То есть, потому что если что-то над локальным кольцом тензора умноженное на k0, то это 0. Поэтому это сюръекция. Здесь есть какое-то ядро, я умножаю все тензором на k. Вот это уже, оно плоское, потому что свободное. То есть здесь получится k на k, вложение.
Это уже известно, как свободно называется.
Да. Здесь 0 будет, потому что это то k и g. Ну и поскольку это вложение, здесь будет, здесь вот это k на k, вложится сюда. Поскольку это изоморфизм, то это нулевое. И опять полим минокаямы,
А прямое слагаемое как раз потому, что это изоморфизм.
Да, и получается, что здесь вложение и сюръекция, то есть это изоморфизм. Поэтому у нас вот дополнение тоже исходит из этого же.
Собираешься этот курс сдавать? Ну, нелегко. А? А у тебя нет? Да, да. Ну, еще хорошо. Категорично. А ты прям взял? Ну, пока нет. То есть нам сказали до конца сентября сказать, что мы берем. Я до сегодняшнего дня думал, что его беру. Сейчас решил пересмотреть свой взгляд на это дело. Ну, буду ходить решать, но возьму что-то другое. У меня пару еще вопросов. Я тут еще буду сидеть. Эксплуатирую? Да, видно, что иначе вообще ничего не понятно.
У меня сначала знал.
А, у тебя тоже?
Ну, просто...
Да, без проблем. Проходите. Мы еще сидим.
Я уверена? Блин. Расписание.
Не, у нас закончено.
Нет. Хорошо.
Можно?
Вторник. Все. Вторник. Семинар математический анализ. 108. Третья пара. Все правильно. То, что никто не пришел, правильно. Я как раз была не доехала. Так, нормально. Надо решать контроль. Сейчас они не поняли. Это под конец года было или? Да. Это был где-то в июне. На самом деле мы уже заметно выбираем. Вот, например, на дифурах было очень свободненько. Ну, блин, по сравнению с 1 сентября. Я пришла, думаю, блин, ну 8 минут опоздал. Не, в принципе, не судьба уже как бы. Автобус опоздал на 2 минуты просто. Я от этого стала на путь. А я пришла вовремя. Сережка еще не вдевалась в телефон. Пицца не готовилась.
Вы на лекции были по анализу вчерашнего?
Да, я была. Так, вспомнить бы. Сейчас. Вот. Значит, мы определили... Так, Коль, извини.
Да ладно.
Мы определили гильбертное пространство, изоморфизм пространств, показали, что любые два сепаратных гильбертовых пространства изоморфны. Дальше...
Да, я его недавно создавал, но я попросил, я зашел в чат, скинул, попросил добавить в таблицу, никто не добавил. Давай. Сейчас, как тебе можно получить?
Ладно, что смотрю, что там поэтому не дадут на семинаре. не знаю,
Я
дадут.
думаю, что на семинаре...
Я, честно говоря, не уверен, что
На
поэтому
семинаре
на семинаре-
опаздывают очень сильно.
Они очень сильно опаздывают, да. И я решил очень сомневаюсь, что нам на семинаре вот по этой даже штуке могут дать что-то глобально новое.
Очень забавная ситуация произошла. Мне человек предложил закрепить ссылку на Google Class. Я не справился с этим,
Не знаю, мы...
Это в настройках как-то можно.
Нет, проблема в том, что он любое сообщение после Google Class закрепить, а именно его не могу. Я не знаю почему. Это очень странно. Я просто не хочу создать себе эту беседу. Я что-то не знаю, какие-то нет. Телефон, так, все.
Ну и все.
Дайте
15
мне
минут, может,
выключить
это произошло.
сегодня.
Да.
Сегодня я не могу.
Да, я ему после
Я
этого
в любой день, кроме сегодня. А завтра можешь? Послезавтра можешь? Послезавтра? Да, давай. Супер. Ура! Ура! Пятница. Мгм. Послезавтра пятница. Нет, четверг. Да. Все равно все хорошо.
Похоже на то. Похоже на семинар Муранов. Если вот так, то вы своего
Сделано.